Welcome you all for this webinar. Myself Girish. I'm a senior member technical staff working for Technologies Private Limited. The title is The Need for Static Timing Analysis in VLSI Design. I'll take you through why we need static timing analysis, how they do it. I also have a lab. I'll take you through how really we do it in the lab. The need for static timing analysis in VLSI Design, why we need, what we do. So with that title, the agenda for today will be what is timing analysis and what is static timing analysis. And I'll discuss where and all we do static timing analysis in the complete ASIC flow. ASIC flow means it starts from Verilog coding to layout, right? Final layout up to there. So where and all we will do STA. Then some common terminologies used in STA. See, I repeat, the what I'm talking today will be the fundamentals, not in depth of STA, right? If you people think you know STA, again it will be a repetition to you, so it will be a fundamentals of STA, right? I'm targeting the freshers, the fresh engineering graduates or the master graduates. So I'll be discussing about the terminologies, fundamental terminologies used in STA. Then I'll take you through what are the timing paths that we need to check, which paths we need to check for timing. Then I will, the main component in any digital circuitry will be a flip-flop, a storing element. So I'll discuss one of the storing element like D flip-flop, which is widely used. What it means, there are something called a setup and hold we need to satisfy. That's the major thing for an STA. So I will talk about what is setup time and what is hold time. Then how do we do setup and hold check? Then how to fix those violations I'll discuss. Then I'll take you through a demo of the tool. The tool that I will be using is a prime time. It's an industry standard tool, more widely used in any industries, right? And it's from Synopsys. And next, I'll be discussing about some other factors that affect the timing. And there are something called as timing exceptions that STA doesn't consider such things. And for those people who are interested to come to VLSI industry, I can take you through. First of all, what is timing analysis? See, if you consider any chip, IC or something, you'll have some input ports to it and output ports. For example, consider in your lab, you might have seen your 7400, 7402, 7432, the basic NAND gate, AR gate, XR gates, right? Or you might have also seen your FPGA, or you might have worked on your 8051 microcontroller, 8086 microcontroller. So it's like a chip, right? It will have some input pins and output ports. For example, if I take 8051 microcontroller, we have 40 pins. One side you have 20 pins and the other side you have 20 more pins, right? So total 40 pins. So there will be one clock pin, one VDD pin, one VSS pin, and many others as input ports in the output ports. So I have taken an example of such an IC here. So there are some 5 input ports. One among them is a clock pin, others are like data pins, and I have some 5 output ports. So definitely some circuitry will be sitting inside it to meet the functionality of the chip. So the chip is designed for meeting the functionality. So then some gates will be sitting. In simple to say, gates means you'll have all your basic gates, AND gate, NAND gate, XR, buffer or inverter, whatever you studied. Along with that, intermediate to store the values, you will have flip-flops. So the way here I'm showing a D flip-flop, right? 2D flip-flops like this. Flip-flops will be sitting, and this will be the reason for logic, and intermediate data will be stored on this flip-flop. Now, what is timing analysis? Say I want my mobile to operate at 1 gigahertz. Will it operate at 1 gigahertz? We need to check it, right? Before releasing it to the market, the developers should need to check whether it will work at 1 gigahertz. I just can't say work at 1 gigahertz. So we need to check it. Definitely all these wires and cells, right? AND gate, NAND gate will have the delay in them. So the delay all put together should be the clock frequency, correct? I am giving some input means that output should come at the frequency set. So I want at 1 gigahertz means I'm giving input and I should get the output at the rate of 1 gigahertz. So RTL people will write the code. You might have also written the codes for full adder, off adder, or counters, right? And you have tested the output. You might have written some test vectors, test benches you might have written in Verilog labs and given input and saw that it is giving the output. You might have also implemented it on FPGA or CPLDs and you might have seen the output, but you might have not checked the timing concept. Timing concept means, will it operate at this frequency? At every 1 gigahertz, will I get the output? So that need to be checked. That is timing analysis. Hope you understood what is timing analysis. I want to check, or I want to see that this IC can work at this frequency, the set frequency. Will it work at 1 gigahertz? If not, I should reduce the frequency or I should think on the logic again and again, so that can I optimize the circuitry and see that it meets the time, right? It meets the time. We need to check that. So hope you understood what is timing analysis means, right? It is just about checking whether it meets the timing or not. Will my output will come at this time or not? With that, what is static timing analysis? Static timing analysis is a method for determining if a circuit meets the timing constraint. I told the timing constraint. Timing constraint means that frequency. Will it work at that frequency or not? The static analysis does not depend on the input values. So, see, you might have written Verilog code and you might have written the test benches. While writing the test benches, you might have given some input vectors, right? So for a full adder, if you want to check, you might have given 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Like that, inputs you might have given and tested whether it works or not properly as a full adder or not. But here, we don't do it. No input values will be given, hence the name static. We don't give any input values, but we will see whether it works or not. The greatest advantage of this is it will check all the paths that are there, for example, if you consider your regular test bench writing the test vectors, right, some paths might have missed, so the data might have not even entered into that path and you might have missed to check that path. But STI is not so. It is very exhaustive, complete. It will check all the paths in the design. Why STA? As I told, it is a complete and a exhaustive verification. It's not like you give test vectors and it will test only the limited portions, not all the paths in the design. So all the timing paths are considered during the timing analysis. But this is not the case in the simulation. When you give simulation, you give vectors, right? Input vectors, and it will test only that path. You are given some input, so whatever gates will come into for that input, right, only they will be tested. Definitely much faster than a gate level simulation, and you don't need to generate a vectors. What I mean by vectors is input numbers. I told you, if I consider a full adder, you want to test a full adder, you need to give inputs a, b, c, in is there, right? So you'll be giving 0, 0, 0, 0, 0, 1, 1, 0, 0, like that vectors inputs you'll be giving, and see what is sum and carry out coming. So that is not here. We don't have a vector generation, and it is faster. This is what we have been doing earlier. As I told you, this is other round, like not an STA. This is dynamic verification, or DTA they call. Here we will have the RTL code, functional simulation. That is what you have done in the Verilog labs. You write test benches. I understand you might have all written Verilog test benches in the lab. So you write a test bench and see whether this works or not. Then I don't know how many of you know, RTL code will be in the is written in the VHDL or Verilog or system Verilog, and it will contain the if loops, for loops, right? And it is not ready to physically implement on an chip, right? You will see only if loop and R loop. I want the circuit to be in the form of gates. So synthesis is a process of converting. This RTL code into gate level code. So synthesis is one domain people work on in VLSI industry. They convert the Verilog code or the system Verilog code into gate level. Gate level means it will contain NAND gate, AND gate. You remember in Verilog you will not write AND gate, NAND gate. You will write for loop, if loop, while loop. So that for loop, if loops are converted to gates. In this dynamic verification flow, even these gates, when you obtain a gate level, you need to go for a simulation. And you do some all other places like placement, routing, clock tree. These are the stages in the physical design to get. I understand you all know what is physical design flow, at least, right? Might have studied about floor plan, power planning, then placement, clock tree synthesis, routing. So at every stage we need to do the gate level simulation in this dynamic verification flow. And this again, you need to generate so many vectors. How many vectors? See, for example, if you consider a number of input ports are 10 input ports, you need to have 2 to the power of 10 input vectors. As example, I told you, if your full adder is having 3 input ports, right, you will have 2 to the power of 3, that is 8. 8 input vectors. You remember 0, 0, 0, 0, 0, 1, right, up to 1, 1, 1. So this many input vectors you need to give. So 8 input vectors. So think of 2 to the power of 10 vectors. That means 1024. So 1024 inputs you need to give and then check it. So it was very time consuming. Now with the gate counts of 10 million, 100 million, they say in an IC, right? So with that huge count, this was not good at all with respect of time. It used to take hours and days to do it. So hence they switched to STA. Now there is no dynamic timing analysis. People won't do it. It is only STA they do in the industry. So coming to where and all we will do STA. So you have RTL code, Verilog code written that will go to synthesis team. They will convert it into gate level netlist. So gate level circuitry will be there. So once the gate level circuitry comes, they need to do static timing analysis. They need to check whether it meeting my frequency or not. See, at this stage, the circuit is not so optimized and the clock tree is also not built. Clock tree means a clock pin, right? We have seen clock, right? From clock pin to the D flip-flops, routing is not done. So we will understand it's an ideal clock. Ideal clock means a proper clock. So at 0 it's rising edge, 5 it's falling edge, means exactly it is. So you might have seen what you mean by ideal, right? So we will assume it as ideal clock tree. And also there is no routing, right? No routing happened between the signal nets. Routing is not happened. With that understanding, I'll do timing analysis and see that my design will reach the said frequency or not. Then this gate level netlist will be obtained. They do some optimization. They will try to shrink the size of the gates, right? Not the number of the logic shrinking they'll do to get the same output, but with less number of gates, they'll try to do it. Then also we will check the timing analysis. Then once the synthesis is done, it goes to the physical design flow. So in the physical design flow, they will do placement of the standard cells. Once they're all placed, again we need to do STA. Then we do something called as clock tree synthesis. Clock tree synthesis means building the clock tree. So you have clock pin. From the clock pin to the D flip flop, the clock is built, right? Actual clock is built during clock tree synthesis. Once the clock tree synthesis is done, again timing analysis need to be checked. Later we do routing. Routing means routing the signal nets, all the signal nets in your design, like A, B, C in is your inputs, right? For a full adder. So A should go to an AND gate, B should go to some XOR gate. All this wire drawing will be done during routing. After that also we need to check for a timing analysis and see that the design is meeting the frequency. So you understood where and all we do the static timing analysis. Some terminologies used during static timing analysis. So same circuit I'll take. Let's consider this as a chip. You have some input ports for the chip and you have some output ports for the chip. And you have the same circuitry I have considered. You have the circuitry inside it. So you'll have chip, input ports, output ports, right? Then this is called a cell. AND gate, NAND gate, D flip flop, buffer. What you're seeing here are all the cells, or we call it as standard cells. So now we're checking for the delay. This AND gate will definitely have some transistors, right? We have all written in CMOS circuit how to write an AND gate, right? It will have some 6 MOSFETs, 3 N MOSFETs, and 3 P MOSFETs, right? So they will constitute for a delay. You agree with that? You give inputs A and B, then it will definitely take some time to give the output. That I'll call it as cell delay. So that will constitute for calculation. I need to calculate the entire delay of the circuit, right? So this is first delay that I'll be considering. So what I mean by that cell delay is, let me take an example of an inverter, right? For an inverter, you are giving the input, so you get the output. So if you give, we know all inverter means if you give 0, you'll be getting 1, and if you give 1, you'll be getting 0. Does it come immediately? I give 0, instantly it will come? No, it will definitely take some time. Or you call it a cell delay or a propagation delay. For example, I had taken here the input from 0, it is going to be 1, right? And you see the output. It is not immediately happening. It is not immediately happening when A is becoming from 0 to 1. Z is not converting to 1 to 0. For 0 input, you have 1 output here. This is 1 output. For this is 0. This is 1, right? So when you're rising from 0 to 1, your output doesn't instantly change to 0, but it will take some time all the way from here to here. Then it will change. Right? So the time taken to this change, we usually measure at 50% of the rise. So So 0 to 1 it is rising, so 50% at the rise, and this is falling, right? So at 50%, off the way of this, at the off way, right? If I consider this, so this is the time, this is my cell delay, this is my propagation delay or the cell delay. Similarly, if I take my input A is changing from 1 to 0 at 50% time, then my output is changing from 0 to 1 at 50%. So this time we will take it as a cell delay, the propagation delay or the cell delay. So definitely an inverter is taking some time to give its output. So inverter is taking some time to give me the output. I can talk more about this standard cells. See, the standard cells like inverter, AND gate, OR gate will come from something called as standard library. It comes from standard library. So people are talking about technology, right? They say 28 nanometer, 65 nanometer, 10 nanometer. What is that nanometer means? You know, inverter is made up of two MOSFETs, one P MOSFET and then one N MOSFET. So two MOSFETs means you will have some MOSFET here. This is your inverter, right? This is your input and this is your output, and this is your VDD and this is your VSS, the ground. So if you consider this, the distance between this is your source and this is your drain, right? The distance between the source and drain is called as technology. So people are talking about 28 nanometer means the size, the length between the source and drain is 28 nanometer. If I say 10 nanometer, it is 10 nanometer. Depending on the nanometer, the technology, the cell delay varies. That is one thing to worry, right? So depending on the technology, cell delay varies. First point. Second point is you can think of threshold voltage. We know threshold voltage, right? Threshold voltage we know. Depending on the threshold voltage also, the cell delay varies. So if lower the threshold voltage, my device will operate faster. I understand you all know what is threshold voltage of a MOSFET, VTH, right? If they are less, my inverter will operate faster. If the threshold is more, voltage is more, it will operate slower. So we will consider second thing as threshold voltages. Then we consider something as PVT variations. PVT variations. What I mean by P means the process variations. The process. See, if while I'm designing this, right, the NMOSFET, I think that this what width of gate oxide are so many parameters here, and I'll consider the delay. But while preparing, it might have not come exactly as what I thought. For simply to say, if you are planning to prepare a chapati, chapati should be circular. So will it come like circular every time? No, there may be some variations. It may not be exact circular. So like that. So if you consider this, right, while designing an NMOSFET, it might be not the way I planned. So there will be variations in the design. So those variations will lead to some other delays, extra delays. So we need to consider those delays. And next, if it is planned to work at 1 volts, the design is entirely planned to work at 1 volts. Somewhere glitches might be there, some voltage variations can be there. So if there are voltage variations, right, so this will affect, all these equations are containing VDD. So the VDD is changing, then timing will vary. So we need to worry about voltage variations also. Then temperature, definitely semiconductors and temperature is so correlated, right? They have a good relationship. So now, if you are thinking that this device or the circuit will work at some temperature, but something happened and the temperature is more. For example, I purchase a mobile to be in Bangalore. It's working fine in Bangalore for a temperature of Bangalore. But I go to some cold regions like Himalayas, there's a temperature change. So my mobile should also work there even, right? So I don't need to purchase one more mobile when I go to Himalayas for a cold region. So that temperature will also have some impact. Hope you understood the cell delay concept. It depends on the technology, it depends on the threshold voltages and the PVT variations. The PVT in simple they call it as corners. Now we have cell delay. We have discussed about cell delay. Then what else? I told you cell delay is obtained from the library. Cell delays are obtained from the library file. I forgot to mention you. The cell delay depends on the input transition. At what rate this is transitioning and what is the load on the output. On both of them, that cell delay depends. So next is we will look into net delays. So you have cell delay. You have a wire, right? Wire means definitely it will have RC values. Wire means it's a resistance. Wire in associated with something else, it will have like a capacitor. So R and C, time delay constant, right? Tau R into C. So definitely this wire will introduce some more delay into my circuitry. So I need to understand what is cell delay and calculate those numbers. I need to understand what is RC values and also calculate the net delay. How do I get this net delay? Is if I have routed the nets, I can do something called as RC extraction, get the real numbers of RC values, and using the expression tau is equal to R into C, I can calculate the time delay. If it is not routed, we do something called as wire load modeling. We model this wire and get the delays. There are some standard numbers. If the wire length is so much, what will be the delay of it if you are not routed? Right? We understood what is cell delay, what is net delay, right? Next is setup time. I will discuss more about setup time. See, you might have also studied what is setup time. This D flip-flop, right? The clock frequency, the clock from the clock pin, you'll get the clock frequency. So you can see by the symbol, it's a positive edge triggered D flip-flops. So whenever a positive edge trigger clock pulse comes, right, an edge comes at this point, we all know how D flip-flop will work. So the data here will be will be sampled means if it is 1 here, it will take it to the Q port. That is what D flip-flop, data flip-flop is, right? What is setup time means? The data which comes here cannot come at any time it wants. It should come well before this clock edge. There's a clock edge, right? Well before this clock edge, the data should have come. I'll have next slide where I'll explain more. So that is setup time. Next is hold time. Hold time means the data is there in the on this D pin, right? One is there. It should not change suddenly. It should not change suddenly and become something else, so that the previous data is yet to sample. So you have a clock edge. Before this, the data should have come. That is called setup time. You have a clock edge. After this, some time, this data should be stable. I repeat, it should be stable. So that is called hold time. If it is not stable for that amount of time, this flip-flop will go to something called as metastable state. Metastable state means you have given 1. I don't know what will be the Q output. It can be 0 or 1. So that will cause me a problem. So in total history of STA, right, we always struggle to meet this setup time and the hold time for every D flip-flop. For every D flip-flop, there will be thousands of D flip-flop in your circuit. So you need to check whether setup time is met or not, hold time is met or not. See, I told you setup time means the data should come here well before this time. So input is coming through AND gate, one more input through AND gate, and through NAND gate you have net delays. The time taken from here to here should be less than this time. And one more, next data should not come so quickly and disturb this data before it is sampled. That is hold time. Now I'll take you through what is timing paths. See, any circuitry and VLSI you take, any chip you take, it will be simply like this. What I mean by simply like this, you will have some input ports and a clock pins like, and you will have some output ports. Inside that you will have a combinational circuit. Combinational circuit, I mean to say, AND gate, NAND gate connected, which really performs the logic. And you will have some D flip-flops to store the intermediate results. You'll have some D flip-flops to store the intermediate results. Considering this input pin and a clock pin as a start points, we divide this entire circuitry into 4 paths. The first path is from the input port to the D pin. To the D pin of the flip-flop is called as input to register path. Input to register timing path. I repeat, input pin to the D flip-flops or flip-flops D pin, the data pin, that we call it as input to register data timing path. That is first timing path. We need to check whether my data is reaching to this D pin in time or not when I'm investigating this path, right? And some input comes, goes into the combinational circuit. This cloud like what I'm showing is a big circuitry where it has your AND gate, NAND gates, right? So that will take some time and gives you the output to the D pin. So the amount taken to here, we need to calculate and see that it meets the setup time and the hold time of the D flip-flop. That is the first path, input to register. Then you have reg to reg path. Reg to reg path starts from the clock pin and through the Q pin, to the combinational circuit and then to the D pin, right? The time taken to go to the D pin, we need to calculate and see that this time delay will be lesser than setup time and also for hold time. One more point to tell you here is the time taken from clock to Q, right? An edge comes at clock pin. The D data which is here should be sampled to Q. There is some time that it takes. D flip flop also doesn't happen all of a sudden. It will take some time. The time is called as TCQ. I have that in the next slide just for your reference here. Then the third timing path is the clock pin to the output pin. The clock pin to the output pin. This is called register to output. Register. This is flip-flop is nothing but register. Register to output port. Then we have the last one from input port to the output port. Input port to the output port, the timing path. Right? We need to see whether my data is reaching in time from the input starting to the output through this path. Right? So summary of this slide is we have 4 timing paths: input to register timing path, register to register, register to output, and input to output, right? And the start points for any timing path will be either an input port or a clock port, and end points for any timing path will be a output port or a D pin of your register, right? Keep in mind these are the 4 timing paths. So what do we check? What do we check in the STA? We check for whether D flip-flops are meeting the setup time and hold time. Then we have something called as recovery and removal for an asynchronous input pins of flip-flops. You know this pins, right? Like reset pin, right? So for them, we do something called as recovery and removal. We have others. I think with respect of time, I'll skip them. Right? We have something called as block getting checked, and we have minimum pulse width. What I mean by minimum pulse width is if you consider a clock, right? So clock should be like a pulse, like right. For some region, it may not be like a pulse anymore. The pulse width can keep on shrinking. So that also we need to take care. That should not shrink, right? Then we have max transition, max capacitance. I'm sorry, with respect of time, I'll leave it for you to study this. You can Google out and make a note of this. You can take a photo if you have a camera, and if you're listening through a laptop or a screenshot you take. Those who are interested can study all others. I will take you in depth of what is setup and hold means. So let's take a D flip-flop. What is it setup and hold? As I explained you, the D data pin that gets the data should be sampled to Q. Right? Setup time is the time the data has to arrive. The data has to arrive to this D pin before the clock edge. Before the clock edge. What I mean, I have here. See, this is my clock pin. The clock is coming at some period of time. So data has come, it has become 1, Now see the clock edge is here and data is well stable. It is 1, very well 1. So this 1 will be sampled and you get the output as 1. Try to understand. Clock edge is 1. So clock edge is 1. So and D flip flop is 1 well before the setup time. I have the setup time for every D flip flop. There will be something called setup time. So before the clock edge, this D should have got the data. So it has got the data well before this. It is only this much time, but it has come so early, right? And it is good to catch. So it will be sampled, and you see the Q output of a flip flop is 1. I can give an analogy. See, if the bus is at 10 o'clock, we go by 9:55, right? We go early by 9:55. We don't go to bus stop exactly at 10. So that 5 minutes is the setup time. Understand? Bus is coming at 10 o'clock. We go and reach early by 9:55 so that we catch the bus. If you go by 10 o'clock, we are not guaranteed whether we will get the bus or not. If I want to go late and okay, let the bus will come at 10 o'clock. I'll reach the bus stop at 10 o'clock. You are not guaranteed. The bus might have come a bit early and might have left, right? So you are not guaranteed. Such case I'm showing here. See, the clock edge is coming here. The data has changed to zero. The data has changed to zero here between the setup time. This is the setup time of the D flip flop, but it is changing from here 1 to 0 at this time. So very late it has come. It should have come at least here, right? So that it should have been sampled. Now my D flip flop goes to a state called as metastable state. Metastable state means you don't know what will be the output. It can be 1 or 0. So you need to take care that none of the D flip flops will to enter into metastable state. If it enters into a metastable state, your chip will operate something like wrong, right? So malfunctioning of the chip will happen. Here I have shown you the good case one more. So it is changing from 0 to 1 well before the clock hits. So the data has been changed to 0 to 1. Hope you understood what is setup time by this, right? The data should come on the D pin much early. That is your setup time. Next, I have hold time. What I mean by hold time. Now see, the same diagram almost. The data has come early. It has been sampled. It is taken to 1. The data here and the D pin is continuing to be 1. Understand this? D has become 1 here itself, and it is continuing to be 1 after the clock edge also. After the clock edge also, there is something called as hold time. For that whole entire hold time period, it is still 1. Then it will be sampled. Then it will be sampled. So this is a good case. What is bad case? Now see, there is a clock edge. This D pin has become 0, 0. So good for setup. It has met the setup time. But it is changing to 1 all of a sudden after the clock edge. It is changing to 1 all of a sudden after the clock edge. After the clock edge. So if it changes to 1 after the clock edge, right? It will not be sampled. It will not be sampled again. So you have metastable state. So it should have actually changed after some time like this, right? So you understand this. The data should come early and also it should be stable after the clock edge. If you don't meet either the setup or the hold, you will your D flip flop will enter into metastable state, right? Am I clear with setup and hold? So let us do a check. How do we check the setup and hold? Right. Consider reg to reg path. For a sample, I have taken reg to reg path. As we had discussed, there are 4 types of timing paths, right? I'll consider one of the timing path, that is reg to reg path. This first D flip flop, we call it as a launch flip flop. We'll call it as launch flip flop, and this as a capture flip flop. The data starts from here. It will enter into combinational circuit. Combinational circuit means you have many AND gates, NAND gates. The data will enter through all those gates and comes as an output. And that output should come well before the setup time of this D flip flop. I repeat, the data should come here and sit well before the setup time of this D flip flop to meet the setup time. So we will check how what all things we need to consider. See, clock edge has started. So clock edge has started and I have a buffer. Buffer, it's a delay element. So because of this delay, the clock will reach to this by sometime late. So I will consider the delay of this as well. I'll consider the delay of this will be considered as T launch. I'll simply write it as TL. So clock has started here. The clock pulse has come. The clock pulse has come here, right? But to reach this, it has taken some time, right? Then after reaching to this, the data might be ready here, like 1, right? So this should be sampled to here. It should become 1. So this 1 to 1 becoming, it will take some time. I call this as TCQ. That's some time that it takes is called as TCQ. Then here now I have one as ready. So this all circuit, right, which is inside this, you'll have gates and the nets. They'll all constitute for a delay. I will call it as T combo or T combinations of a circuit. So what is the time taken? TL TCQ plus T combo. By the time it will reach here. right? It is like you woke up in the morning to go to the bus stop, you will do some, right, regular activities, and you get ready and you reach the bus stop. The time taken to see your phone, waking up early in the morning, you see your phone, right, for WhatsApp message. That is the first thing that we are all doing today. So see WhatsApp messages which have come in the night is TL, like woke up, right? Some regular activities in the morning is TCQ. You have your breakfast, right? Walk up to your bus stop. All this is your T combo, and you have reached the bus stop, right? Did you reach by 10 o'clock? What time you left? Did you reach well before 10 o'clock is the time? 9:55 I should have reached. So this will be the TL plus TCQ plus T combo will be the total delay, plus this, what is this, T setup, I'll call T setup. So if I add all this, right, it should be like for 10 o'clock. You agree with me? If I add all this, you started at, let me take this clock pulse. Your mom made you to wake up at 8 o'clock in the morning. So you had taken so much time, and you might have reached, including this T setup, means 5 minutes of time, right? 5 minutes of time. All add put together should be 10 o'clock. Hope you understood. So then only you have reached the setup. If not, if this is not adding to 10 o'clock, if it becomes 10:05 or something, you have missed the bus. So for that, the expression. So as I explained you, the T launch, TCQ, T combo, right? Combination circuit and T setup. All put together should be like 10 o'clock. How much it should be? It should be less than, see here, this is the time, right? Clock edge has come. Clock edge has come here. So the time taken, this is like 10 o'clock for me. So you have taken all the time to reach up from here to here. So you might have reached by 9:55 something, right? So it should be less than TP. The TP is your clock period. So TP is your clock period, right? And even that during the path also there might be some delay taken on the bus to come, right? There might be some traffic and it has been delayed. So it might have come by 10 o'clock plus some minutes. So that is T capture. The path clock reaching to this is called T capture. So this all put together should be less than TP plus T capture. T capture is the in the capture path. This is called as capture path. The delay in this path is called T capture. So if you understood that, I have next is hold checkup. What do you do for a hold checkup? See now, we have seen that you have come at 9:55 exactly, like, but you should not leave the bus stop so early so that you don't board the bus at all. So you need to check that, right? So how do you check this? Again, the same time, the T launch and TCQ T combo all put together should be greater than T hold of this and the T capture. I don't know to what extent you are able to understand this. Hold is somewhat bit hard to explain, or I can give you some analogy. Okay, I'll give you some analogy. You have come meeting the setup time. You reached here by 9:55, and you are waiting for to board the bus, right? One of your friend started from home, right? He comes so early. You still, it's not 10 o'clock. You are about to board the bus. You are about to board the bus, right? Your friend comes in and and throw you away, and he will stand in the bus stop. This is like that, right? You are standing in the bus stop to board the bus, as we have seen here, right, in this diagram. So what I mean, so you have come well in time, but your friend makes you 0 to 1. He will change. In place of you, he will stand. Actually, 0 should have been boarded, but it has changed to 1 by this time. So it should have been still for this time. Then only it would have been captured. Otherwise, it is entering into metastable state. So when I'm explaining the hold, right? So this time, the next your friend comes should be greater than the T hold time. If it is greater than that, then you will be boarding the bus, right? You will be boarding the bus and your data will be captured. Same calculations. I thought I'll give you an example and give you time to calculate this if you understood properly. With respect of time, I think I'll not be able to take you through the tool demo if I do this calculation. See, simply I'll show you how to calculate this. We have the expression, right? Considering the expression, this expressions we discussed. So clock frequency will be given 500 megahertz. We will convert this into period. So it will be some 2 nanoseconds. Now see, there's a delay here, TL, zero point 0.1 nanoseconds, 0.1 nanoseconds. I'll show you the answer. So T launch, 0.1 nanoseconds. TCQ is one more zero point 0.1 nanoseconds I have taken. This combinational circuit, if it operates faster, it will take 1.9. Slower means 1.9, faster means 1.2. So I need to consider the slower version of this. So T combo is 1.9 plus T setup. T setup for this D flip-flop will be 0.2 nanoseconds. So all put together is my data arrival time. You arrived at the bus stop, right? That is called data arrival time. What is data required time? Data required time is TP, the time period, plus T capture. TP is, we know from the clock frequency, 2, then T capture is this delay, zero point 0.1 and 0.1, 0.2 nanoseconds. So 2 plus 0.2 nanoseconds, 2.2 nanoseconds. Now see, actually the data required time is 2.2 nanoseconds, but data arrived at 2.3 nanoseconds. So that means if we calculate the slack, we call it a setup slack, which is required time minus the arrival time. If you calculate, it is coming to minus 0.1. Here you can strictly see this is violating, right? 2.3 is lesser than 2.2. No, it is not. So it is violating. So we call setup is violating. This circuit will not operate at this frequency. So we need to think of bringing the time lesser. This 2.3 should be at least 2.2 to meet the setup time. Similarly, I have a calculation for hold. I think we will share this PPT with you people, right? Then you can do the calculations and check. So I have calculated for hold similarly, and here if you see the hold is been meeting by 1.1. So hold is fine in the circuit, but setup is failing. So how to fix the problems? You have seen just now. This is 2.3, right? So if it becomes 2.1 or 2.2, this will be fixed. So we can talk, right? Instead of going to the next slide. See here, this zero point 0.1 nanoseconds. If this is a buffer, if this is unnecessary, can I remove this? Can I remove this buffer if it is an unnecessary buffer? So if I remove this 0.1, this 0.1 will go off. If this 0.1 goes off means it will become 2.2. Then you have met with the setup. Understand the concepts. If I remove that unnecessary buffers, it will meet, right? Or if I have some circuit in the combinational circuit, some high threshold voltage gates, as I discussed in the beginning, high threshold voltage gates means they'll take more time. Let me replace them with the low threshold voltage gates. Then also the time will reduce, right? Like that, we will work out and reduce it. See, I told you adding or removing buffers will reduce the timing. Replacing the buffers with two inverters. You know, two inverters means it's a buffer. Inverter connected back to back is a buffer. So we can play around replacing a buffer with an inverter. If this buffer can be replaced with a two inverter, we can replace it and see the timing calculations. That is one way to do. We call it as changing the drive strength. The drive strength means this is capable of driving so much fan out. Hope you know what is fan out. So I can increase the fan out of this, drive strength of this, so that it will work faster. That way also we will work. And one more is, as I told, VT swapping. VT swapping means threshold voltage, right? We will change the cells with respect to threshold voltages, then it will operate faster. Okay, I will take you through a demo. See, this is how we invoke the tool. This is a industry standard tool, the prime time. Prime time is the tool that is extensively used in industry to perform. So I have invoked the tool. It is from Synopsys. If you are new to VLSI, right, we will have something called a script like this. This is a script to run the tool, right? So we need to mention in the first part where the libraries are, the cells, the standard cells, right? AND gate, NOT gate, where they are there. So we should mention the path, right? Then we will read the Verilog, the code for on which you want to do the timing analysis. That will be read, right? And you'll also read the constraints, that what is clock frequency, all that you will read. Then this is the part where I am reading the RC parasitics. RC means R and capacitance and resistance values are read, right? Sorry, with respect of time, I need to rush it, right? We read all them. Here in the prime time, this is the tool. We will say source. I'm reading all the commands that are there in that. We actually don't do this way in the labs regularly. We will read one by one. So now you have the a tool which has read all the design into it. This is what STA people work. I'm clearly telling you, this is what STA people will work. So we will see this. See, this is the circuit, a big circuit actually. This is a circuit that I am showing you the demo now. So some counter, some big counter. So you will have some input ports and you will have some output ports here. You can see flip-flops will be sitting here, right? And some gates are all there. What I was showing, right? A simple, right? These are all routing nets that are being routed, right? Cells are there. So net delays, cell delays, what I was talking. So you'll see circuit like this. It will be big circuit actually. I'm just zooming and showing you some parts of it, right? If you go, right? So that is what the circuit is for me. So there is one more thing that really affects my timing is something called as crosstalk. Crosstalk is, see, you have a net here. This NOT gates output is going to some NOT 3 output and buffer output is going to something, right? If these nets are very closer, right? Definitely you saw big circuitry. Nets are very closer. So when there is very close, right? We know capacitor, right? A conducting plate and a conducting plate with an insulator, you have a capacitor formed. So now if there is a rise here, this output of NOT gate makes travels from 0 to 1, right? When it is traveling from 0 to 1, it will impact this closer net. This closer net, right? Actually, it was like only 0 always, but because of this rise, even this got a glitch. Even this got a glitch. This is called victim net. Glitch, I mean to say, it should have actually been 0. Because of this guy, it is changing from 1 to 0. Sorry, 0 to 1 it has changed for very short period of time. This short period of time to 1, right? This might come all the way to D sometimes and make this output to go to 1. Actually, it should have been 0, but because of this guy, this has become 1. I hope you understood this concept. All right. So we need to check uh, in what cases this is happening and try to avoid all this. Under this crosstalk, we have so many things to discuss. This is actually called rise glitch. One of that rise glitch. This is right. We have many more. This because of this delays of the cells will also get impacted. I'm sorry again with respect of time. Make a note of all this. Study all this. What is this? You have so many blogs written by many people, right? Understand what are all this. What do you mean by overshoot, undershoot, right? I think I discussed this already. PVT variations, process, voltage, temperature. See, if this is the die, right? This is the wafer which we have seen in our engineering subject, right? There are so many gates or ICs sitting here. So due to process variations, there can be variations in the device. So because of that, your delay varies. I discussed it. Even because of voltage also, voltage, if it is more voltage, delay will be less. If it is less voltage, delay will be more. And with respect to temperature, more the temperature, more will be the delay. Less the temperature, lesser will be the delay. So based on that also, this also we need to consider while designing your circuitry. Just to introduce what are timing exceptions. Timing exceptions are the ones which my STA tool does not consider for timing calculations. For example, a false path. False path is a path which really does not do any logical operations like, but for some reason it is sitting in the circuitry, right? For example, simply I can say, consider a mux, right? Mux 2 is to 1 mux. So two inputs, one select line. See, if select line is changing from 0 to 1, then your inputs also going to the output. But if you fix your select line to 0, fix your select line to 0, what is the output of this mux? Always the first line, correct? Never, second line never comes into picture. You understand? Consider a mux. Select line is given always 0. Then output will be always the first one, I naught, whatever you write, I naught. So output will be always I naught. So the second path, I1 to output, is not there at all. So this is called false path. So my STA will ignore these paths, will not report these paths. Then we have something called as multi-cycle path. I had shown you the path right now. We expect all the paths to operate in one clock period of time, in one clock period. I mean to say 500 megahertz means 2 nanoseconds. So all the operations should happen within 2 nanoseconds. For some reason, the circuitry may be too big, and in some regions, that may take more than 2 nanoseconds. They are called multi-cycle paths. And for that also, my STA will not consider. So we need to set something, tell the tool that this is a multi-cycle path, and then only my tool will respect that multi-cycle path. With that, thank you all for joining. I'm ending the session. Thank you.